Welcome to System on Chip Design Series. We are discussing hardware-firmware interface. In this video, we are going to discuss about event notification. In an embedded system, hardware and firmware have their respective jobs to do, right? But they must work together as a system. There must be some coordination between the hardware and firmware, and if they are not uh, communicating well and coordinating, so the system is said to be out of balance. Okay, so it will directly impact the performance of the system, the way firmware is waiting for the hardware to finish something, and if the hardware is waiting for firmware to say what to do next. So these kind of things we have to deal. Okay, so if the firmware has to wait for hardware to complete a task, in the meantime firmware often do something else with other tasks. Okay, so but if the hardware does not generate any kind of task completion signal, firmware has to often guessing whether it is done or not. Okay, so either it has to go and check very often, or it has to just blindly wait for some random delay and see whether the work is done or not. Okay, so in this video, we will discuss about the event notifications, like from the hardware, what kind of event notifications are there, depending on the situation. Okay, so here we are discussing how firmware determines when to proceed with the next step. Okay, here we have to find a balance between the hardware and software. Okay, so that we will get maximum performance from both firmware and hardware. There are multiple methods, okay, for firmware to wait what to do next. Okay, so first one is no indication. Okay, in this case, like it don't once the task is handed over to the hardware, it never waits for any indication. Okay, it simply uses it initiate the task, and it immediately proceed for the next task without waiting for hardware. So the risk here is it may lead to inefficiency. Okay, you don't know what happened with the task which you hand over to the hardware. Okay, so earlier we saw in our previous video, we designed an Axelite based adder where we simply write register A and register B, and simply we are reading some register. Okay, so there we are assuming it is done already by writing both registers. But if it is more complex than an adder, okay, it will take some time to do the processing. So in that case, next step is you wait for a random delay. Okay, it's like firmware waits for a period before proceeding. Okay, it simply assumes the hardware completes the task within that delay. Okay, but here the risk is like you're wasting some time. Okay, say like hardware is very quick and doing it fast. Okay, but since it's waiting for a fixed period, it's like you are creating a C program running at the driver level, and you just program it to wait for a fixed period. Okay, so it will waste cycles if the delay is too long. Okay, hardware may not be ready if the delay is too short. So you have to find a balance between those two. And the third one is we should have a status bit where firmware will check the specific bit by the hardware. Okay, so it's like time delay method only, but instead of waiting too long or too short, first it will wait for some time and come back and check this status bit. If it is done, then it will continue with the other thing. If it is not done, it may wait for another period of time, and then it can continue checking the status bit. Okay, so it's very common method, this is called polling. Okay, it's a very common method in the embedded systems, and it's like reliable. Okay, so the example here is hardware sets a done bit that firmware can poll from a register. Okay, say in our example, if we design an adder such that like you provide the inputs and you just give a start bit. Okay, and the hardware responses when the result is ready. It may take like next cycle or 2 cycles, it doesn't matter. It will say like done, and it will write into another register. Okay, and the firmware can come and read this status bit. If that bit done is set, okay, it is hardware is assumed to be done correctly, and it can proceed with the other thing. So, and the fourth one is the interrupt. Okay, so in previous method, like so firmware is keep on polling the register, or that means in other words, it's keep on reading the done register. Okay, if it is not done, again it will wait for some time. Okay, so there also it is waiting for some random time, which is a wastage of cycles. Okay, so that was solved in the fourth method. Okay, hardware actively signals firmware to proceed. It's like once the task is start, firmware will go and do some other task. Okay, meanwhile hardware completes the task and set the status bits like done and other things, and interrupt the firmware. When the process gets the interrupt, firmware can come and read the status bit and do the follow up. Okay, so this is like a very common method. Okay, interrupts, so that like there is no waste of firmware cycles. Okay, it's similar to third thing, except it will give a interrupt. So again, these are the analysis, like we can compare these four things. When there is a no indication, it's risky for complex tasks, because hardware may not be able to do within the specified. Okay, even time delay method, it's easy to implement, but it reduces the efficiency of the firmware, because it keep on waste timing cycles. Okay, and third one is status bit register, which is reliable and but may require a continuous polling, which is again a wastage of firmware cycles. Okay, last one is efficient, but we have to be very careful with how often a system can be interrupted. Okay, say in some cases, say you are working on a receiver, like you are receiving some data from the external network. Okay, because of some system issue, like for every packet you receive, if you get a interrupt, it's not a very optimal design, because uh, usually like you will get millions of packets per second, right? So in this 1 second you will get, if the hardware is trying to interrupt the firmware like million times, it's again it will reduce your performance. Okay, so yeah, here the best, we have to see the best of all these things. Okay, we have to select which method to follow based on your system requirements. Okay, and we should be like a consistency for other blocks also, so that like you will get a optimal performance for all those things. Okay, so like continuing to this thing, like we can see through a demo. We reuse our previous example, Axelite adder, where I will show you the time delay and status bit. So interrupt part, maybe we'll discuss in future video, where we discuss the interrupt generation. Let us see a demo of these concepts. Let us continue the previous example, Axelite register, Axelite adder design, where we are going to use status bit. Okay. So earlier, this is our register definitions, register map, where we have A and B as the input operands, and sum is the result. So let us define one more control register, which is 1 bit wide, which will tell the start, and we are defining access as like software will come and set this bit, and hardware will acknowledge this start, then it will be cleared by the hardware. So that's what this RW1 is. So from the CSR, the hardware will be like one output and one clear input. Let us go and implement this register map. Then let us see what is created. So now we have, apart from A and B and some input and output ports, now we have two more ports from the control. One output from the CSR, which will give the start, and from the hardware we acknowledge by clearing this port. So let us go back to our Accelerate thing. So this is how I defined the handshake between the those two ports. So I defined as a start, which is a control bit from the CSR, and I defined acknowledgement for. Okay, so when there is a start is accepted, we will do the operation. Then we acknowledge the start as well. Okay? So those two ports I connected here. Let me run the design. Okay, so let us open this GTK wave, uh, accelerate adder.fh. So this is how the like bunch of accelerate registers. Then when we write a 1 to the start bit, so there is a assertion, the start signal is asserted. Okay, then immediately we are doing the operation, and we are acknowledging the thing. So I'll go back to the test and show what we did. Okay, so here I write A and B registers with 1 and 2 respectively. Then I write 1 to the start bit. Okay, then I am reading back the register, and expect that should be cleared, because the in immediate cycle we are acknowledging the start, so the register will go back to 0. Then after that I am reading the result register, which is sum of A and B, which I am setting comparing with the expected value. So that is what I showed in the waveform. Okay, so yeah, in this case we are acknowledged in the next cycle. So with this we are concluding this video. So we compared 4 methods. Okay, and I showed a demo of the status bit and delayed time. Okay, so we discussed the best practices of this event notification. Okay, so next steps are like we'll see the performance optimization techniques for a SoC design.